Hello everyone. In this lecture, I am going to discuss the topic active high pass filter of the subject integrated circuits. Contents are active and passive filters, first order and second order high pass filter. Then after I will discuss higher order filters. So starting with the basic term filter. So as the name suggests, it filters out something. What is this something? In this case, filter means to pass a particular band of frequency which is desirable and blocks the other frequencies. Blocking means attenuate the other frequency. So filter is a circuit which passes a desired range of frequencies and blocks the other frequencies. Mainly filters are of two types. One is active filter and the another one is passive filter. In passive filters, only passive elements are used. It means that passive filters are made up of three components. One is resistor R, another one is inductor L, and the third one is capacitor C. So passive filters are the filters which are made up of passive elements, for example resistor, capacitor and inductor. And as far as active filters are concerned, active filters consist of active element, and mainly we use op-amp as an active element. Since op-amp contains transistor, transistor is an active element. Along with op-amp, we use resistor and capacitor. So we can say that active filter, it is the combination of operational amplifier, op-amp, resistor and capacitor. It is called active filter because op-amp is an active element. So on the basis of the components used, these filters are classified. There are advantages and limitations of active filters and passive filter both. The main advantage of active filter is that active filter, it provides gain. This is the main advantage of active filter. It provides gain. The reason is that it contains active element. That active element op-amp, it amplifies the signal. That's why we say that active filter provides gain. But passive filter, it does not provide gain, because passive filter is made up of only passive elements and passive elements cannot amplify the signal. So this is the first advantage of active filter over passive filter. That advantage is active filters provide gain, while passive filter, it does not provide gain. In fact, in passive filters, the signal is get attenuated. And another advantage of active filter is there is no loading problem. There is no loading problem. The reason is that in operational amplifier, we normally use non-inverting configuration in filters, in active filters. So non-inverting configuration of op-amp, it gives high input impedance. That's why the loading problem is reduced in case of active filter. So these are the two main advantages of active filter. The first advantage is it provides gain, and the second advantage is there is no loading effect in active filters. And obviously, the drawbacks of the passive filters are it attenuates the signal and there is loading problem in passive filters. But there is one advantage of passive filter also. That advantage is passive filters are used at high frequencies like radio frequencies. Fine. We can use passive filter at radio frequency. The reason is that passive filter, it consists of inductor, but active filter, it does not use inductor. Passive filter, it uses inductor, and we can use inductors at high frequency, at radio frequency. We don't use inductors at low frequency, that is audio frequency. The reason is that at low frequencies, at audio frequency, the size of the inductor becomes very bulky. That's why inductors are not used at audio frequency. Inductors are used at radio frequency. That's why that is the advantage of passive filter. That advantage is passive filters can be used at radio frequency easily because the size of the inductor is reduced at high frequency. right? So that is the advantage. And as far as the disadvantage of active filter is concerned, we can say that the gain, bandwidth, product and slew rate of the active filters are limited by op-amp, because in active filters we are using op-amp. That op-amp it is having limited bandwidth, it is having limited slew rate. If it is having limited bandwidth and slew rate, then obviously the filters which we are going to design using that op-amp, that will also have limited bandwidth. Fine, that is the limitation of active filter. So active and passive filters both have advantages and limitations. So it depends upon the application, but normally we prefer active filters because it provides gain and because there is no loading problem. But it is not like that we don't use passive filters, because passive filters are used at high frequencies. So this is all about the classification of filters. Now the types of active filters. Types of active filters, there are 4 types of active filters. The one is low pass filter, high pass filter, then band pass filter. 4th one is band reject filter. And apart from these 4 filters, there is another filter called APF, that is all pass filter. And the 6th one is a KHN filter, that is also called universal filter. So this KHN filter, it consists of all filters. We can realize low pass, high pass, band pass and band reject filter with the help of KHN filter. As far as all pass filter is concerned, all pass filter, as the name suggests, it passes all the frequencies. So the question is that why it is called filter? If it passes all the frequencies, then why it is called filter? Actually, the characteristic of all pass filter is that it changes the phase. It compensates the phase. For example, when the electrical signal, when it propagates along with the transmission line, then the phase of that signal is changed. So in order to compensate that phase, we use all pass filter. So all pass filter changes the phase, not frequency. Fine. So these are just the classification of filter. In this lecture, we are just focusing on the high pass filter, and obviously we are focusing on active high pass filter. Active high pass filter, it means that we will be using an op-amp. Along with the op-amp, we will be using resistor and capacitor. So starting with the high pass filter. So high pass filter, so firstly I will discuss first order high pass filter, HPF, first order high pass filter. So we will see that why it is called first order. So firstly, we need to understand that what is high pass filter. High pass filter which passes high frequencies and it blocks the low frequencies. So to understand it, we can draw the frequency response of high pass filter. So in the frequency response, on the x-axis there is a frequency, at the y-axis there is a voltage gain in dB. Voltage gain in dB. So the frequency response of the high pass filter is like this. So we can see here that at low frequencies the gain is less. The gain is less. It means that that signal is being attenuated, that signal is being blocked. But at the high frequencies the gain is highest, and this highest frequency is called the passband gain, AF. And here there is very important term called cutoff frequency. That cutoff frequency is called FL. This cutoff frequency, it is also called minus 3 dB frequency. It is called minus 3 dB frequency because it is the frequency at which the voltage gain, it is reduced by 3 dB of the maximum gain. So this FL is the cutoff frequency. This cutoff frequency, it is also called minus 3 dB frequency. It is also called corner frequency. It is also called brick frequency. So in this graph, there are 2 bands. This one is called pass band. Since the gain is higher, that's why it is called pass band. And this one is called stop band. So we can see that in pass band, the voltage gain is highest. In the stop band, the voltage gain is reducing. Fine. Stop band means the signal is getting attenuated. The signal is getting attenuated. In the pass band means signal is passed. If signal is passed, it means that we will get gain. That's why in the region where we are getting the gain factor,
That's why that band is called pass band, right? So we can see we can say that in a high pass filter, the frequencies above FL it is passed, and frequencies below FL it is blocked. Fine. So as far as the roll-off rate is concerned, the roll-off rate is 20 dB per decade for the first order high pass filter, and for the second order high pass filter it is 40 dB per decade. Similarly, for third order filter it is 60 dB per decade. So as far as the circuit is concerned, for first order high pass filter, first order obviously it is a active high pass filter. So here we are taking operational amplifier which is having two input terminal, one is inverting, another one is non-inverting. To provide the filter function, what we do, we connect a capacitor at the non-inverting terminal, and along with this capacitor there is a resistor also that is connected between non-inverting terminal and ground. So this is C, this one is R, and the input signal is applied at this RC section. Now you can remember the first order low pass filter. If you remember that in the first order low pass filter, just this RC are interchange. So in that lecture I had discussed it that to design first order high pass filter, you just interchange R and C in the first order low pass filter, you will get first order high pass filter. So the function of this C and R, it is used to provide the filter function. Filter function, that means high pass function. And to get the gain, what we do, at the inverting terminal we connect two resistors, one is R1 and another one is RF, that is connected in the negative feedback path, and the output is V out. So this is the circuit of the first order high pass filter. So in the first order high pass filter there is only one RC section. You can see that one RC section is 1C and 1R. Similarly, in the second order high pass filter there will be two RC sections, 2C and 2R. Fine. So this is the circuit for the first order high pass filter. Now you can derive the voltage gain transfer function for this first order high pass filter. For that, let's take the voltage at the non-inverting terminal is V1. Now you know the relation between V out and V1 since it's a non-inverting configuration. So what will be the value of V out? V out will be equal to 1 plus RF upon R1 into V1. Now from voltage division rule you can calculate the value of V1 in terms of Vin. So that will be equal to R upon R plus 1 by SC into V. Now just put this V1 into the above equation, and after that put S equal to j omega and omega is equal to 2 pi F. Fine. After doing this, you can get mod V naught, mod V out upon Vin, that is equal to AF upon under root 1 plus F by FL square, but in the numerator there is one more term, that is F by FL. So this is the voltage gain for the first order high pass filter. If you compare this equation with the first order low pass filter, then in the first order low pass filter, in the denominator there is F by FH square. There is FH in low pass. That FH is the cutoff frequency of low pass. Here FL is the cutoff frequency of high pass. But also there is one term multiplied with AF, that is F by FL. So this is the voltage gain of the first order high pass filter, which you can simply calculate. Just put V1 into the equation of V out, and from there just put omega is equal to 2 pi F, and of course this AF is the passband gain. This AF is equal to 1 plus RF upon R1, 1 plus RF upon R1. So you will get 1 plus RF upon R1. Just replace that 1 plus RF upon R1 with AF. Fine. So this is about the first order high pass filter. Now come to the design problem of first order active high pass filter. So how we design first order active high pass filter. So firstly I am going to discuss the design steps, and after that I will discuss one numerical based on first order active high pass filter. See, the design steps are almost same like you have done in first order low pass filter. Fine. So step 1 is firstly decide that for which cutoff frequency you are going to design that filter, FL. Normally in the numericals, FL is given.
In step 2, we need to consider some value of C. Normally we take C less than or equal to 1 microfarad, but try to take the value of
C which is available in the market, like 0.1 microfarad, 0.01 microfarad values are available. Fine.
And after that, use the equation of cutoff frequency FL, that FL is equal to 1 upon 2 pi RC. So here one thing I want to mention here. This FL is, in this equation of voltage gain, this FL is equal to 1 upon 2 pi RC. Right? This 1 upon 2 pi RC,
it is also there in the first order low pass filter. Fine. So before listening to this lecture, I would suggest that first refer the lecture of the active low pass filter. Fine. So when you
solve this equation, this one,
when you solve this equation,
so you will get the term 1 upon 2 pi RC and 1 plus RF upon R1, right?
Just replace 1 plus RF upon R1 with
AF and 1 upon 2 pi RC with FL.
After replacing this,
you will get V naught upon V, V out upon V. Fine. Now from here, we know the value of FL from step 1. We know the value of C from step 2. Here you can calculate the value of R. Step 4 is find out the values of R1 and RF
which provides gain.
For that, use the equation of AF, that AF is equal to 1 plus RF upon R1.
We are getting 1 plus RF upon R1 because we are using non-inverting configuration, right?
So normally AF is given in the question, in the numerical for the first order filter, and one equation, 2 unknown. What we do, we normally take R1 less than or equal to 100 kilo ohm. Fine. You can take any value of R1 and put that R1 into this equation and calculate the value of RF. And lastly,
design the circuit of the first order active high pass filter and mention all the component values in that particular circuit.
So these are the design steps of the first order active high pass filter. Now coming to the numerical problem. The question is design. You have to design a first order high pass filter which is having cutoff frequency of 1 kilohertz and passband gain of 5, and also draw the frequency response. So go with the step by step. So step 1 is FL. What is the value of FL? 1 kilohertz. So it is given in the numerical. In second step, just decide, so just select some value of C. Let's take C is equal to 0.1 microfarad. Step 3 is calculate the value of R. We know the equation of FL, that is the cutoff frequency, that is 1 upon 2 pi RC. So from here, what will be the value of R? R will be equal to 1 upon 2 pi FL into C. So from step 1, you can put the value of FL 1 kilohertz, and from step 2, you can put the value of C 0.1 microfarad. So from here, you will get the value of R. In the fourth step, just find out the value of R1 and RF. For that, use the passband gain equation, that is 1 plus RF upon R1. In the question, AF is given, that is equal to 5. So what will be the value of RF upon R1? It will be 4. So from here, RF is equal to 4 into R1. So let's take R1 is equal to 10 kilo ohm. Then what will be the value of RF? It will be 40 kilo ohm.
So from these 4 steps, we have calculated all the component values R, C, R1 and RF.
Lastly, just draw the circuit and mention all the component values. So we know the circuit of the first order high pass filter. So we connect RC section. So this is not R. In fact, this one is C and this one is R. And we apply the input signal at the capacitor in the high pass filter. And at the inverting terminal, we connect 2 resistors R1 and one resistor, another resistor RF in the negative feedback path. Fine. So this is the circuit of the first order high pass filter. Just mention the value of R1, RF, C and R. Like C, we have taken 0.1 microfarad. R1 we have taken 10 kilo ohm. RF we have got 40 kilo ohm. and you can calculate
R yourself, right? So mention all the values, component values. So what is the relevance of this circuit? The relevance is that if you design this circuit on the breadboard in your lab by taking these component values, right? And when you draw the frequency response practically in the lab, then you will get the cutoff frequency of this filter approximately 1 kilohertz. So after that, you have to draw the frequency response also. So to draw the frequency response, you have to make a table like you have done it in the numerical of the first order low pass filter also. The first column is the frequency. Let's say frequency F is in hertz. Then calculate the value of V0 upon Vin. Since at y-axis the voltage gain is in dB, so convert this ratio into dB. For that, take log and multiply with the 20. Right? Now take some values of F, but definitely take the cutoff frequency 1 kilohertz and few frequencies below 1 kilohertz and few frequencies above 1 kilohertz. For example, you can take 100 hertz, 200 hertz, 500 hertz, similarly 2 kilohertz, 5 kilohertz, fine. And you can calculate the value of V0 upon Vin. You know the equation for V0 upon Vin. You have derived it that this V0 upon Vin is AF into F by FL upon under root 1 plus F by FL square. Now what is F? F is the frequency of the input signal. FL is given in the question that FL is 1 kilohertz, and AF is also given, that is the passband gain, that is the value of 5. It is given in the question. Now put the value of F in this equation and calculate V0 upon Vin with the help of calculator. After that, convert that ratio into dB. And finally, you can draw the frequency response, that is the graph between frequency and voltage gain in dB. So when you will join all the points, then your graph will be like this. Fine, high pass response. So this is a numerical problem. Like you have to draw the frequency response in this numerical, although you know the frequency response graph, but you have to draw with the help of this table, with the help of these calculations only, right? So you can do these calculations yourself. It is very easy. You have to just use calculator and you will get all the values. Fine. So this is the approach to solve the first order high pass filter numerical. Now coming to the second order filter. So second order active high pass filter. Second order active high pass filter. Like you have studied first order active high pass filter, similarly you can design second order active high pass filter. What do you have to do? You have to just use 2 RC sections. Fine, you will get second order high pass filter. Or you can also draw this circuit with the help of second order low pass filter. See, in the circuit of second order low pass filter, just replace resistors and capacitors. Just interchange resistors and capacitors. You will get active high pass filter, second order active high pass filter. So let's draw the circuit again. At the non-inverting terminal, see, firstly start with the inverting terminal. To get the gain, what we do? We connect 2 resistors at the inverting terminal. One is called R1 and another one is called RF. Fine. So with the help of this R1 and RF, we are getting the gain, right? And output is, let's say, V out. Now see, the input signal is V. The input signal is V, and one capacitor and one resistor we are connecting like this. Now see, if you apply this V directly at this RC section, CR section, then it will be a first order high pass filter that I have already discussed. Now in the second order high pass filter, what we do? We use 2 RC section. So you can see that at the board, there is one RC section, CR section, RC section, right? Now we have to add one more RC section. We will connect one more capacitor and one resistor is connected in the feedback path. Right now, this V is applied at this capacitor. Let's say this capacitor is C1, this is C2, and let's say resistors are R2 and R3. So this is the circuit for the second order active high pass filter. Now just compare this circuit with the second order low pass filter. First refer second order low pass filter circuit, right? So in the second order low pass filter circuit, you have to just interchange R and C. Now similarly, this is the circuit of second order high pass filter. If I say that draw the circuit of second order low pass filter, what you have to do?
You have to just replace this C1 and C2 with resistors and R2 and R3 with capacitors.
You will get second order low pass filter. So
this is the circuit, and when you do the derivation part and when you calculate the voltage gain for this circuit, you will get AF upon under root 1 plus FL by F to the power 4. So this is the voltage gain of the second order
active high pass filter. In the denominator, FL by F to the power 4 term is there. And what is F? F is the frequency of the input signal. That input signal you have applied here. And FL is the cutoff frequency of the second order high pass filter. AF is the pass band gain, right? And for second order filters, for second order low pass and second order high pass filter,
we take the value of AF that is equal to 1.586, right? Because this value of AF gives the Butterworth response. Butterworth response. What is Butterworth response? What is Butterworth filter? Butterworth response or filter is the response or filter which gives flat pass band. Which gives flat pass band. So when you draw the frequency response of the high pass filter, what you want? You want this gain should be constant in the pass band. You don't want variation in the pass band. You want constant gain, right? Flat. The graph should be flat in the pass band. So to ensure it, the filter should be Butterworth. And to ensure that the filter is the Butterworth, for that we take AF is equal to 1.586. This thing we had done in the second order low pass filter also. Fine. Now we have to design the second order filter. For that we are going to do this problem. And this problem is this numerical is you have to design second order high pass filter, and the cutoff frequency is given, that is 5 kilohertz, right? And the pass band gain is not given. Normally in the second order low pass and high pass numericals, pass band it is not given. Normally it is not given, but it is given, then you have to take that value only. But if it is not given, then in the second order low pass filter and second order high pass filter, you have to take AF is equal to 1.586. Fine. So start with the step 1. In step 1, FL should be mentioned. FL is 5 kilohertz, that is given in the question. Step 2 is you have to take the value of capacitor. Here we are using 2 capacitors, but for mathematical simplifications, what we do, we take C1 equal to C2 equal to C. Let's take C is equal to 0.01 microfarad. Step 3 is you have to find out the value of R2 and R3. Again, for mathematical simplifications, what we do, we take R2 equal to R3 equal to R. And we will use the equation of cutoff frequency FL is equal to 1 upon 2 pi RTC. We get this FL equation for second order filter only when if we take C1 equal to C2 equal to C and R2 equal to R3 equal to R. When we take these approximations, only then the cutoff frequency of the second order filter is equal to 1 upon 2 pi RC. Fine. So what will be the value of R here? R will be equal to 1 upon 2 pi FL into C. From step 1, you can put the value of FL. From step 2, you can put the value of C. Here you can get the R value, and that R is equal to R2 equal to R3. And in the fourth step, find out the value of R1 and RF. For that, use the equation of AF. Since we are using non-inverting configuration, so the passband gain AF equation, it will be equal to 1 plus RF upon R1. See, as I have already mentioned that in the numericals of second order low pass filter and second order high pass filter, normally AF value is not given. So in that case, always take AF is equal to 1.586 because this value gives the flat passband gain, that is called Butterworth response. From here, what will be the value of RF upon R1? It will be equal to 0.586. From here, what is RF? RF will be equal to 0.586 R1. Fine. Now take value of R1 less than 100 kilo ohm. Let's take R1 is equal to 10 kilo ohm. So similarly, you can calculate the value of RF. So from step 1 to step 4, we have calculated all the component values. So in the last step, what you have to do? You have to design the circuit. You have to just draw the circuit and you have to mention all the component values. So in step 5, what you have to do? In step 5, just draw this circuit of second order high pass filter and mention all the component values R1, RF, C1, C2, R2, R3, right? And the problem will be completed. Now, you have to draw the frequency response also here, right? So to draw the frequency response, the step will be same. That is, again, you have to draw this table, and in the first column, there will be frequency F, let's say it is in hertz, and you have to calculate V naught upon V in for different frequencies, and you have to convert this voltage gain in ratio into dB, that is 20 log mod V naught upon V. Just take few frequencies and don't forget to take the cutoff frequency, and cutoff frequency is 5 kilohertz. Then take few frequencies lesser than 5 kilohertz and few frequencies above 5 kilohertz. We are doing this to draw the graph properly. So let's take F is equal to 100 hertz, F is equal to 1 kilohertz, 3 kilohertz. Similarly, few frequencies above 5 kilohertz, let's say 6 kilohertz, 10 kilohertz, right? And just calculate the V naught upon V in here with the help of calculator and convert that V naught upon V into dB. And what is the equation for V naught upon V? This V naught upon V for second order high pass filter, it is AF upon under root 1 plus FL by F to the power 4, where AF is the pass band gain, AF is 1.586, FL it is given in the question, this FL is 5 kilohertz, and F is the frequency of the input signal, that is this one. So after completing this table, you can draw the frequency response and you will get the frequency response like this. And of course, the roll-off rate, it will be 40 dB per decade for second order. For first order, it is 20 dB. For second order, it is 40 dB per decade. And at x-axis, there is a frequency. At y-axis, there is gain in dB. Although you know the frequency response of second order high pass filter, but you have to draw the frequency response with the help of this table, because this table you have found for this particular numerical, for a particular cutoff frequency, right? So this is all about the first order and second order high pass filter. Now coming to the higher order filters. See, if I say that design third order low pass filter, if I say that design fourth order low pass filter, so how we design those filters? See, we have studied first order low pass and first order high pass filter, and after that we have studied first order high pass and second order high pass filter. So with the help of first order and second order filters, we can design higher order filters. Let's say if I say design third order filter, third order low pass filter, what you have to do? To design third order low pass filter, you will take first order low pass filter and you will connect it in cascade with second order low pass filter. This is input V and this one is the output V naught. So this structure will give third order low pass filter. Similarly, to design fourth order low pass filter, you can cascade two second order filters, two second order low pass filter. If you cascade two second order low pass filter, it will become fourth order low pass filter. Similarly for high pass filters. So higher order filters can be simply designed by cascading first order and second order filters. Now there is some advantage and disadvantage of higher order filters. To understand it, we need to draw the frequency response. At x-axis there is a frequency, at y-axis there is a voltage gain in dB. Now take the example of first order low pass filter. So first order low pass filter, the frequency response is like this, and the roll-off rate for first order low pass filter, it is minus 20 dB per decade. Similarly, for the second order low pass filter, the roll-off rate will be minus 40 dB per decade. For third order low pass filter, the roll-off rate will be minus 60 dB per decade. For fourth order low pass filter, the roll-off rate will be minus 80 dB per decade. So what you are observing here, you can see that as the order of the filter is increasing, the stop band response, this is the stop band response,
stop band response is approaching the ideal response. So
the ideal response of the low pass filter is this one, right? This one is the ideal frequency response for the low pass filter. Now you can see that as the order of the filter is increasing from first to second to third to fourth order, the stop band response, it is approaching towards the ideal response. So that is the advantage of higher order filter. That advantage is as the order of the filter increases, the stop band response, it approaches towards the ideal response. That is the advantage. But the limitation of higher order filter is that as the order of filter increases, the number of components required will be more, the circuit will be complex. You can understand it. If you design fourth order low pass filter, then you will be requiring 2 second order low pass filter. Then of course, the number of components will be increased, the complexity of the circuit will increase. That is the limitation of the higher order filters. But the advantage is the stop band response, it approaches towards the ideal response. So here we need not to go in detail of the third order low pass and fourth order low pass because the concept is same. You just need to cascade the first order and second order filter to design higher order filter. That's why first order and second order filters are very important to understand. It is very important to understand the first order low pass and second order low pass and first order high pass and second order high pass, because with the help of these first and second order filters, you can design higher order filters like third order, fourth order, fifth order, etc. So this is all about this class. So in this class, I have discussed about the active high pass filter, first order high pass and second order high pass filters, and we have done numericals also, and I have discussed the concept of higher order filter.